again, this is a presentation that my colleague, Dr. Rahi Rabari, should have been here to present, but as David explained, he was unable to come due to his visa restrictions. So, University of Sheffield got involved in two key aspects of Work Package 3. So, firstly, we were involved looking at controllable factors of overhead lines. So, we carried out some modelling, looking at factors such as wire tension. But as I'll go on to explain, we also looked at a novel design of the overhead line system, which could potentially be a low-cost system. And as Tudor explained, we also got involved in task 3.5, which was the validation of the overhead line accelerometers. And the work that Tudor has been doing, developing those sensors, it has really added to the project. To be able to gather such acceleration data from the catenary, well, it's quite novel, and as far as I know, it hasn't been done before, and had a lot of risks putting sensors on the high voltage system. So, going back to the modelling work that Rahi carried out at University of Sheffield, so we started off by modelling a typical catenary system. We had a previous model that had been developed at University of Sheffield, which had been developed in ANSYS, and it was then converted into an LS-DYNA model. And yes, it has already been validated. The original model had already been validated, so we validated our LS-DYNA model against the data for the previous model. We then looked at, with the finite element model, we initially started looking at controllable factors such as wire tension, trying to understand the impact of reducing tension, what that has on the dynamics of the contact wire. And then we looked at using a trolley wire model. So trying to develop a much simpler overhead line system. So it doesn't, as you can see, it's a much simpler system compared to the catenary system. And it has been proposed quite a lot in the past that this could potentially be used for mainline railway, well, for lesser used, low speed mainline railways. So we wanted to investigate that further. So, so the models were created. So I don't know whether these are a video. No. So created the model. We validated it at train speeds up to 60 meters per second. And what we saw was that within the model for the, so we validated the catenary system model, but we also modelled the trolley wire system and found that with train speeds up to 60 meters per second, the overall contact wire system remained stable enough up to those speeds. So, in addition to the modelling work, as Tudor explained, we also upgraded some of our test facilities at the University of Sheffield in order to be able to test the overhead line accelerometers. So, we took one of our existing rigs which we'd used for fatigue testing of some of the neutral section elements, and so this is the old rig, and upgraded the actuator that we used on that rig. So went from a hydraulic actuator to an electrical actuator, which gives us a much better dynamic response on the rig. So it allowed us to test at a whole range of different frequencies. So this is the video, I think it's the video that stopped. It should be a constant frequency. So it allowed us to simulate different overhead line conditions, and then obviously to test the overhead line accelerometers, and there they are in situ. We can get outputs from the actuator. So this was very interesting that we could actually take the waveforms from the actuator and then be able to compare it to the acceleration from the accelerometer data from 2DAS sensors. And it gave us some really interesting results as well. You could see some of the additional frequencies that we got on the catenary wire, but also as you stopped the actuator, you could see the natural frequencies of the overhead line. Okay, so, and obviously you've already seen the results of the sensors from 2DAS presentation. Okay, thank you very much.